cover Chapter 9, which is the last chapter covered in our course before the final exam. We're going to knock out Part 1 today, Experimental Design and Analysis Between Subjects Designs. Let's get back to some basics that we discussed pretty early on in the semester. So pretty generally, how do we know when one thing causes another? Well, luckily, we have 3 criteria for causation. First, our cause must be related to the effect. Second, the cause must precede the effect. And third, no other explanations must exist for the effect. Let's talk about some of the advantages of true experiments. What are some things that correlational and quasi-experimental designs are lacking? Well, with correlations, we can't really control anything. We're simply assessing the degree of a relationship between 2 observed variables. For quasi-experimental, we're observing naturally occurring groups, and again, we're not controlling or manipulating really anything. So the biggest advantage of true experimentation is control, which is directly related to our 3 criteria for causation. Now a little bit more review. Independent and dependent variables. We've been talking about them since pretty early on in the semester, so it should be second nature to you how they are defined. Your independent variable is what gets manipulated, and your dependent variable is what gets measured. So just a little review here. If we have the research question, does sun exposure cause plants to grow taller? Our IV would be sun exposure, and our DV would be plant height. If we had the research question, does birdseed color affect how much birds eat? Our IV would be birdseed color, and our DV would be the amount birds eat. If we had the research question, does a new mosquito repellent cause less mosquito bites? Our IV would be the new mosquito repellent, and our DV would be the amount of mosquito bites. Now, I know that's pretty basic review, but it's been a minute since we talked about independent and dependent variables. I just wanted to get you guys back in the swing of talking about them. So now let's talk about a between subjects design and what it is. Well, specifically, it's a type of experimental design. Here are the main characteristics of experimental between subjects designs. First, you always have mutually exclusive groups, meaning different people serve in different conditions. You wouldn't have someone participate in the experimental group and the control group. So each participant only participates in one of the 2 groups, not both. Next, you have to have an independent variable with at least 2 levels. 2 levels simply means that the IV is expressed 2 ways. So the first way being we don't manipulate the independent variable in the control group, which gives us a baseline or a standard. And the second level of the IV would be the manipulated independent variable level given to the experimental group. Finally, a between subjects design must have at least one dependent variable, one variable that is measured. And typically this is using continuous data, so it's on a continuum. There are many different ways that experimentation involves control, and we're going to cover some of the more important ways in this class. So first, we can control who is in our study. It's ideal to conduct random sampling from the population. So random sampling, just in review, means that everyone in the population has an equal chance of being recruited into our study. This allows us to ensure that our sample is representative of the population. And we need our sample to be representative because we want to generalize back to the population at the end of our study. Next, we can control who participates in our conditions. And we do this by using random assignment. Now, random assignment is a little different than random sampling because random assignment means that each person has an equal chance of being assigned to one of the two conditions. By using random assignment, we are able to make our two groups or our two conditions as equivalent as possible. So all participants have an equal chance of being in either condition or receiving either level of the independent variable. We can also control what is happening during the experiment. So remember, with correlations and quasi-experimental studies, we can't control very much. But in an experiment, we can control almost everything that happens during the experiment, with the exception of how the participant will respond. So we may ensure that all things are equal during the experiment. Procedures that a participant follows are the same. The experimenter treats every participant the same. We can even control the environment in which the study is given. So in true experimentation, we will control when the informed consent is given, what time the participant starts the study, how long the study lasts, when the manipulation is given, how long is the manipulation given, how long between the manipulation and the actual measuring of your DV. All of these things are done very systematically and in a very controlled way. So what happens if we do all of these things in our experiment? The level of the independent variable is the only thing that is different across the groups. We can conclude that the independent variable causes the change in the dependent variable. We've eliminated all other possibilities that we can. So let's take a look at an example. And this should be pretty familiar if you guys did something like this for your second homework assignment. So let's say that you hypothesize that daily quizzing causes higher grades in Psych 3010. How would you design an experiment to answer this question? Now, there are many right answers here, but since we're delivering the course in this format, I thought that I would give you more of a straightforward example to work off of. But know that some of these things can be changed. Experiments can vary from researcher to researcher, and this is just one way that we could design an experiment to answer this question. So first, our independent variable. What are we going to manipulate here? Well, we're testing the effect of daily quizzes on grades in 3010. So we would manipulate our daily quizzes. That would be our independent variable. Now your dependent variable, what you are measuring, in this case, it is your grade in 3010. So we're trying to see how daily quizzes affect grades in 3010. Now we need to identify who is going to be in our experiment. In general, we want Psych 3010 students, right? So we're talking about grades in research methods and statistics, not grades in all psychology classes, just specifically Psych 3010. So we want to make sure that our sample includes Psych 3010 students. Now, who receives the level of the independent variable? Well, the experimental group would receive the daily quizzes, and the control group would get no quizzes. To control other factors in the experiment, we could, of course, use random sampling from all the Psych 3010 students available. We could randomly assign all of those students to our two groups. We could follow the same procedures, make sure the quizzes are the same, make sure the material is the same, the grading scale is the same, all things like that to ensure that we have control. Let's take a look at another example. So you hypothesize that more exercise causes less stress. How would you design an experiment to answer this question? For your independent variable, what would you manipulate? Well, here we're testing the effect of exercise on stress. So our independent variable would be exercise. Our dependent variable, or what we would measure, in this case would be stress levels. We're trying to determine how exercise affects stress levels. Now let's identify who is going to be in the experiment. Well, in this case, we don't really have a hypothesis that is specific to a population. We're just saying that in general, we think exercise causes less stress. So we would randomly sample the entire population. Now, who receives the levels of the IV? Well, your experimental group could, for example, take part in daily exercising, while your control group does no exercises. You could even go as far to say that your experimental group will exercise for an hour a day and your control group only exercises for 15 minutes. So here you could vary your levels of the IV depending on your research question. Now, there are many ways we can control factors in our experiment. We've already randomly sampled the population. We'll want to make sure that we randomly assign our participants into our experimental and control groups. We can ensure that the experimental exercise is the same for everyone, so what type of exercise, how long it lasts. We could control many things in this example. Now let's talk about a few different design types. So what is a post-test only control group design, other than a mouthful? Well, a post-test only control group design is an experimental design in which the dependent variable is measured after the manipulation of the independent variable. So with a post-test design, you will have equivalent subjects in both groups. You give the level of the IV to each group, then you measure post-treatment. And what happens if we see a difference on the post-test? Well, we can conclude that differences are due to the level of the IV received and not by some third variable. But let's take a look at an example of how this actually looks. So you have the research question, does weight loss coaching encourage weight loss? So let's say you want to use 50 participants and you randomly sample them from the population. You will then take your 50 participants and randomly assign them into your two groups, your experimental group and your control group. Then you would administer each level of the IV to your two groups. So your first level of the independent variable for your control group could be no weight loss coaching. Your level of the independent variable number 2 for your experimental group could be weight loss coaching. Now let's say because it's a weight loss study, we want to wait about 6 weeks before we take our final measure on weight. And then we measure the DV for both groups after they've received the level of the IV. So in this case, we're measuring weight. Okay, now let's take a look at another example. This research question deals with the effects of block studying on final exam score. So you randomly assign 100 participants from the population into two groups, your control group and your experimental group. Then you administer the independent variable to each group. For your control group, your level of your IV1 would be normal studying techniques. And for the experimental group, you'd have level of the IV2 block study techniques. Then you would measure both groups after the independent variable is administered by taking their final exam grade. Now there are some concerns with post-test only control group designs. You have to ensure that your manipulation is valid, and this can be tricky with some research. For example, if you're testing the effects of daily quizzes on exam scores and your students are consistently absent, you may not have enough data or quizzes to run your statistics at the end of your study. Additionally, you have to worry about the dependent variable being measured consistently and reliably. We talked a lot about reliability and validity a few weeks back, so you should be able to see why ensuring that our dependent variable is measured the same way every time for every participant is important. Next, we have the pre-test, post-test control group design. So everything is the same here, but you add a pre-test. That way, the dependent variable is measured twice for all people. We measure it once before the independent variable and once after the independent variable. In post-test only designs, we assume that our groups are equal before we administer the independent variable because we've randomly assigned them. But that's really the only way we can be sure that they are equivalent. With a pretest, you know if they are equivalent or not before they receive the level of the independent variable. Now, there is a disadvantage in that participants may catch on to the point of the study and adjust their natural behaviors, such as only paying attention to the information that was on the pretest. However, this doesn't happen a ton, and we do a few things to protect against this. Like in some situations, we may administer the pretest days or weeks before the actual experiment begins. So let's take a look at how this plays out. So here we have the same research question: does weight loss coaching encourage weight loss? Only this time, we're going to take the 50 people that we randomly sampled from the population and pretest all of them. So we're going to take their weight before the study begins. Then we will randomly assign the participants into two groups, the control group and the experimental group. Then we will administer our independent variable. So either no weight loss coaching for our control group or weight loss coaching for our experimental group. We're waiting 6 weeks, and then we will take their final weight. We'll measure the DV for a second time. Now we can really get a sense for how much weight it can be accounted to the weight loss coaching. Let's take a look at another example. So, do brain training games increase working memory capacity? So let's say that you pre-test all participants that you've recruited from your population and you give them a working memory test. Then you randomly assign your participants into your control group and your experimental groups. Then you're going to administer your levels of the independent variable. So level 1, no brain training games for your control group. And level 2, brain training games twice a week for your experimental group. Then you would measure the DV for a second time after everyone has received the independent variable. So in this case, a working memory test. Okay, so we've been talking about confounds all semester. We're going to take a final look at what they are and why they are important again. A confound is an uncontrolled extraneous variable or flaw in the experiment. Confounds make it extremely difficult to say that changes in the dependent variable are due to the level of the independent variable that the participant has received. Our goal is to minimize, if not eliminate, all confounds in our studies and maximize our control. Individual differences may still occur even with random assignment as a result of chance, but that's where pretesting can be beneficial and helps us determine if there are any differences that are existent before the experiment begins. I thought this was a nice graphic to again just represent the relationship between your independent, dependent, and confounding variables. So your independent variable causes the effect or outcome in your dependent variable, and confounding variables are any other factors that are affecting this relationship. So here are some examples of confounds. The temperature in the experimental classroom might be higher than the control. The time of day differs in the control and experimental classrooms. The experimenter may be nicer in one condition than the other. Perhaps the gender is different across therapists. Or the experimental group gets more credit in SONA compared to the control group. So you can see how each one of these things could cause our participants to react differently, right? So we want to control as many of these things as possible. We want to make sure the temperature is the same in the classrooms, as well as the time of day that the study is administered. You want to make sure that the experimenter is equally nice in both conditions. Perhaps you want to make the gender consistent across therapists. And we always want to make sure that all participants, both in experimental and control groups, are getting the same amount of SONA credit for their participation. So we're going to discuss internal and external validity, and this is the last big thing we'll cover content-wise in this course. So internal and external validity. First, just a reminder of what validity is. Validity is a measure of truthfulness of a measuring instrument. It indicates whether the instrument measures what it's claiming to measure. Now we're going to look at two types, internal and external validity, and specifically why confounds threaten internal validity. So, internal validity is the extent to which the results of an experiment can be attributed to the manipulation of the independent variable rather than to some confounding variables. So, confounds decrease internal validity. The best case scenario that we always aim for is that we have no confounds, so there's only one explanation for our findings. To do so, we need to be aware of some threats to internal validity. The first being non-equivalent control groups. Are the control and experimental groups the same in every single way except the manipulation? Self-selection into a study is a big issue, especially when we're using systems like the SONA research site. Some participants are able to immediately participate in a study, while some students may have to be placed on a wait list if the study is full. The waitlisted students may perform differently or even become aware of study conditions than those who were able to willingly sign up themselves. So how do we guard against this? Well, we always randomly sample from the population, and then we want to use random assignment. That way, those waitlisted students and the immediate access students are equally distributed between the two groups. Next, we have the threat of instrumentation issues. This is most likely a faulty instrument, so meaning our tests are not reliable. Changes in our dependent variable may be due to the measurement instrument and not to the changes in your independent variable. The best way to guard against this is by piloting your measure. So this means testing your measure on a separate group of people before your study to ensure that it works as it should. You can also ensure that you have an equivalent control group. If you have an equivalent control group, then you should only see changes in your experimental group and not in your control group. Next, we have attrition or mortality. Most of the time, this is not an issue because participants in both groups, the experimental and the control, will drop out equally. Some studies make attrition more of an issue though. For example, if participants are asked to watch a sensitive video or stop using a common medication in the experimental group, they may drop out more frequently. In extreme cases, you may see where flooding therapy is being used on phobias, and people drop out of this pretty rapidly because they can't handle the flooding of their phobia in the experimental group. So if only our experimental groups are getting things like the flooding or the true manipulation, they might drop out at a faster rate than the control group, and this makes the two groups unequal. We can guard against this a little by making control groups again as equal as possible, so that if attrition is the issue and it relates back to our manipulation, we should only see that in the experimental group and not in our control group. So having an equal control group gives us the ability to clearly see that. Next, we have diffusion of treatment. So this is when information contamination from other participants that have already completed the study occurs. So a participant tells their friend about the experiment, which causes reactivity issues with the incoming participant because they know the gist of the study, if you will. We protect against this by running large groups of participants in very short time frames. We also ask participants not to discuss the nature of the study with others during debriefing. So as you may recall, debriefing occurs at the very end of the study. Researchers will let participants in on what the true nature of the study was and how their participation was important. If you've ever participated in a study where you were debriefed, you probably were asked not to share any details of the study with anyone else, and this helps us guard against diffusion of treatment. Now lastly, we have experimenter effects. So this is when an experimenter's expectations bias their judgment or actions. So perhaps the experimenter is nicer or gives more feedback to the experimental group than the control group. This could mean that changes in our dependent variable are a result of how the experimenters are treating their participants, not our independent variable. The best way to guard against this is by using single and double-blind experiments. So what are single and double-blind experiments? A single-blind experiment is an experimental procedure in which either the participants or the researcher are blind to the manipulation being made. Double-blind experiments are experimental procedures in which neither the participants nor the experimenter knows the condition in which the participant has been assigned. Both parties are blind to the manipulation. We aim to conduct double-blind experiments as best we can. So as a researcher, I may have a research assistant be the one actually interacting with my participants, and that research assistant may have no idea who is in which group. So again, a single blind study, the participant doesn't know what condition they are in, experimental or control, but the researcher is aware which group they're in. A double blind, the participant doesn't know what condition they are in, experimental or control, and the researcher doesn't know what condition the participant is in. So why does this matter? Internal validity is highly threatened by experimenter bias. Even if experimenters try their hardest not to be biased, they still could be unknowingly. So if the experimenter is unaware of which condition a participant is in, then they simply cannot be biased. So I made a visual example of this to kind of show you what this looks like. In a single blind experiment, we would have a researcher who knows which participant is in which group, so the placebo control group or maybe the treatment experimental group. However, the participants are blind to which group they are in. With a double-blind experiment, you have the researcher here is unaware of which group the participants are in. So neither the researcher or the participant is aware of who is getting what treatment. We also have some threats to external validity, but first let's go over what external validity is. External validity is the extent in which the results of an experiment can be generalized, specifically to people outside of your study. So there are just a couple threats to worry about with external validity, or at least for the purposes of this course. First, we want to be able to generalize to populations. So we've talked about this, especially with our introduction to inferential statistics. Our main goal here is to sample the population, conduct an experiment, and then be able to generalize those results back to the population. So can the results of our study be generalized beyond the subjects in the actual study? The college sophomore problem is a great example of this. A mass amount of research conducted at universities includes samples of primary college sophomores. Sophomore and junior classes tend to ask for more research participation compared to freshman or senior classes. This means that the majority of our participants are college sophomores, and it's a little difficult to relate college sophomores back to the entire population. College sophomores generalize to the college population perhaps, but not really our entire population. We guard against this by trying to randomly sample populations, not just universities, and sometimes we'll replicate a study on a new sample to ensure results extend to the general population. So for example, we may conduct a study on the SONA research site, and then we want to replicate that in a new setting. Well, Amazon Mechanical Turk is a platform that allows professionals, everyday Joes, students from all different campuses to participate in research for monetary reward. So sometimes you may first run your study on SONA, and then you want to replicate that on something like Amazon Mechanical Turk to see if your results generalize to other populations. Next, we have the threat of generalization from laboratory settings. So can we actually say that these results that we found in our study will occur naturally outside the lab setting? An example of this is the toy task problem. If you bring children into a lab and ask them to play with toys that they have never seen before, they will behave differently than if they were playing with their own toys at home in which they are familiar. So again, we typically try to replicate lab findings in a more natural setting to be able to generalize outside the lab. So this is just kind of a visual of the relationship between internal and external validity. External validity is everything happening outside the study. Does the same effect occur in different settings? Internal validity is what's done inside the study. Was the research done right? So again, I just wanted you to see the relationship between the two. Okay, so now let's answer this question. Is this a threat to internal or external validity? You are taking a social psychology course that requires SONA participation in research studies. You find out that a research lab in the department is offering a study on gambling. When telling your classmate, they tell you that you should definitely sign up for the study. It was fun. They then proceed to tell you how the study was conducted and that they learned in debriefing that the researchers are curious if people will pick red cards over black cards. You decide to sign up and participate in the study. When you're participating, you're sure to equally choose black and red cards, and you're happy to receive your SONA credit when you're finished. So is this a threat to internal or external validity? Well, specifically, this is a threat to internal validity. Even more specifically, diffusion of treatment. By your classmate telling you what the gist of the study was, you reacted differently, which is going to mess with the results of the researcher's study, right? It's going to threaten the internal validity of our study. So let's look at another one. A researcher for the NCAA is curious how college athletes communicate with one another when their coaches and or trainers are not around. They decide to conduct a study where they randomly sample college athletes from different colleges and assess their communication behaviors. The athletes will be asked to hang out with one another in a laboratory setting for 1 hour. Researchers will be observing via live video feed. The researchers will then code the communication for patterns. So is this a threat to internal or external validity? Well, this is a threat to external validity, specifically generalization from laboratory settings. Here they had the athletes come and hang out in a laboratory setting for an hour. I think it's pretty safe to say that college athletes are going to behave differently in a laboratory setting where they're hanging out in comparison to, say, the locker room, the bus, at practice, in classes, in the dorms. So here it may be hard to generalize these findings from a laboratory setting to a naturalistic environment.
All right, the last thing we'll cover in this course is how to conduct a t-test for independent samples. We'll cover what it is and what type of experimental design you should use it with. And here's a hint, it's what we've been talking about this entire lecture. So a t-test for independent samples is the statistic that we use for between subjects designs. In between subjects designs, each subject is randomly assigned to be in either the experimental or control group, one or the other, not both. And this relates to the ways in which we form our hypotheses for between subjects designs. So we've discussed hypothesis testing a lot in the last few weeks. You should be pretty well practiced in it by now. But let's review the 4 steps we've learned and how to apply them to the t-test. So for a non-directional hypothesis in which we have no prediction about the direction of the relationship, our null hypothesis will state the experimental group will not differ from the control group. And our alternative hypothesis will state that the experimental group will differ from the control group. But these are non-directional, and we're not making a prediction about how they will differ, just that there will be differences present between the two groups. Now for a directional hypothesis, where we have an idea of the direction between the variables, we're going to take a look at an example from the table in your textbook in Chapter 9. I'm so sorry I don't have that page number up, but it's the main table right there in Chapter 9. So for our null hypothesis, for a directional hypothesis with between subject designs, For this example, we'll say the spaced practice group will not do better than the massed practice group. And our alternative hypothesis will be that the spaced practice group will do better than the mass practice group. So here we have a direction. We expect one group to do better than the other. So we use a directional hypothesis. Now, step number 2 is finding our critical value. And because we're doing a t-test, this is our t critical value. So what alpha level will we use? Well, we always set our alpha level to 0.05, and we'll determine our critical value by looking at the table on page 433 in your textbook. You will need to know your degrees of freedom, and for a t-test, our degrees of freedom are always determined by adding together n-1 and n2 minus 1. So for our example, we'll use 10 minus 1 plus 10 minus 1, which is 9 plus 9, or 18. If you look in the table, you'll see that the t critical value for 18 is 1.73. So those are the first 2 steps. We've determined our hypotheses, and now we've found our t critical value. Next, we will calculate our t observed. As always, you'll be given this formula, but you will have to know how to use it. And I've also included the information that you'll need to complete the formula. So remember that x bar is the mean for each group. So x bar 1 is the mean for group 1, and x bar 2 is the mean for group 2. Then we have S1, which is our standard deviation for group 1. S2 is our standard deviation for group 2. And then we have our N. N1 is how many subjects were in group 1, and N2 is how many subjects were in group 2. So let's break this down a little bit. Let's start with our numerator up top. We have x bar 1 minus x bar 2. So we have 22 minus 16.9, which gives us 5.1. And that's it. It's pretty simple to do the top part of the equation. But let's look at that denominator. It can be a little intimidating, but we'll go through it step by step, and I promise it's a lot more simple than it looks. So for S1 squared, you're going to take your standard deviation and square it, which gives us 4.45. For your standard deviation for group 2, you'll square it, and that gives you 6.30. Basically, it's the variance for each sample. That's how we determine it, by squaring our standard deviation. Then you're going to divide your variance for sample 1 by n, the total number of participants. You do the same thing for your second standard deviation squared and your second n. And then you add those values together, and most importantly, you have to remember to take the square root of that value. So let's look at that. Here we have our top portion again for you. So the mean difference between your 2 groups and your actual sample is 22 minus 16.9, which gives us 5.1. Then you're going to take your standard deviation squared for group 1 and divide that by n1, so 4.45 divided by 10. Then you'll take your standard deviation squared for group 2 and divide that by the n for group 2, which is 6.30 divided by 10. You're going to add those together, which gives you 1.08, and then remember to get the square root of that value, so 1.04. So then that gives us 2 numbers for our numerator and denominator. You have 5.1 divided by 1.04, and that would give you a t observed value of positive 4.90. So take a second, go back through that math, make sure you're able to work this out the same way. One key piece of advice, make sure you're using PEMDAS. Don't try to just plug all of this into your calculator, break it down, go step by step, and you should get a t observed value of 4.90. Now, our next step is applying our decision rule and talking about what that represents. So compare your t observed to your t critical value. Do you reject or accept your null hypothesis? Well, our T observed was 4.9. Our T critical was 1.73. So in this case, we reject our null hypothesis. The mean difference appears to be greater than you would expect by chance alone. The spaced group was better than the masked group. And you can say this another way. There is a very, very small chance that we got such a large effect, or in this case, a mean difference, due to chance alone. Now, just to note a couple of things about our T statistic, there are several things that can contribute to a larger effect or a larger T statistic. First, we have larger mean differences, so that would give you a larger numerator. Less variability of raw scores would give you a smaller denominator. An increased sample size would also give you a smaller denominator. So make sure you have these three things jotted down to better understand how they can contribute to a larger effect or a larger T statistic. All right, so that's it. That is your last lecture for this course. Make sure that you reach out with any questions. We covered a lot today. This is a very in-depth chapter. However, I have complete faith that all of you will do wonderful with all the assignments related to Chapter 9. You do have 2 sets of practice problems related to independent sample t-test. The first set is just for practice. However, the second set you can submit for 5 bonus points in the course if you wish to do so. So if you're working on those and you have any questions, feel free to reach out. You also need to complete your lab for this week. So it's our last lab. Go through, knock that out, and again, reach out with any questions you may have. And if you have any trouble, again, any questions, if anything is confusing or you need any clarification, just reach out and I will help you just as soon as I can. So thank you, and y'all have a good week.